but I'm discussing lots of details. So you can go through those 20 pages and get some more insight of some of the side discussions that we have. If I take any of these equations, they are really 3 equations in one, because that's a vector, right? That's Ex, Ey, Ez, and this also another vector, 3Ex, Ey, Ez, Hx, Hy. If we take either one of them and discuss, for some reason, we always get more comfortable working with the electric field rather than the magnetic field. Psychological, right? Background. So, del squared Ex, Ey, Ez is equal to minus omega squared mu epsilon Ex, Ey, Ez. So you can separate that into 3 separate equations. Del squared Ex is equal to minus omega squared mu epsilon Ex. Typically, again, we feel something unique about E sub z because that's the direction of propagation. Although, as we will learn later, that it's not E sub z, right? But anyway, minus omega squared mu epsilon E sub z. So if I solve any of these, I'm solving the others in basic concepts. How do you solve this equation? Well, basically, what we do is we assume that the E sub z is a function of all 3 coordinates. So, in reality, that's a function of x, y, and z. And also, function of x, y, and z. We use a technique called the separation of variables. If you have a function of variables and you don't expect any interaction between those variables, then you can assume your function to be the product of 3 separable functions. I'm trying to remember what did I call them. I can't remember what I called them in my notes. Fx of x only times function of y only times function of z only. It's a product of 3 separable functions. So that's the separation of variable technique. So that's an assumption. And put that in. So you differentiate that del squared, and we'll do it in Cartesian coordinates because, like I said, the rectangular guide is going to be the one that will be worked with initially. When we go back to the circular guide, then we have to use cylindrical coordinates. But for now, let's use rectangular coordinates. So the del squared is what? Second derivative with respect to x squared, plus second derivative with respect to y squared, second derivative with respect to z twice again. So you differentiate that twice with respect to x, you end up with fx double prime times fy times fz is equal to minus omega squared mu epsilon fx fy fz. I forgot to add here, I'm sorry, plus there's more to the left hand side. You differentiate it again with respect to the y, you end up with fx fy double prime fz, and here you end up with fx fy fz double prime. And then we divide through by fx fy fz. What do we get? You end up with fx double prime divided by fx plus fy double prime divided by fy plus fz divided by fz minus omega squared. Now we know that fx is a function of x only, so this is a function of x only. This is a function of y only. This will be a function of z only. So this term here is totally independent of this, totally independent of that. You have three independent quantities added to each other, and the right hand side is a constant. Now, if I come to this class here, and I pick three independent people, and I ask each one to shout a number, and I claim that the numbers they independently shout will add to a constant, would that ever work? No way, right? Unless these individuals are going to shout constant numbers that I know, right? And they are going to be always shouting the same number. But if you pick any number you want independently, obviously there is no way this can happen unless each of those is a constant itself. Independent constants. Not quite, because they add up to a constant here. So there's some dependency of these constants. They depend on each other. So I'm going to give them some names. Since this is a square thing and also a second order differential equation, f double prime, a constant times fx, right? Solution for that is what for? Before we give a name to the constant, we have to think about what kind of solution are we going to get. So it's a function now that you differentiate twice, you get back the same function. Right? Here it is. You differentiate it twice, you get back the same function. Multiply by constant. Exponential. Or sines and cosines, which are cousins. Right? Exponentials of an imaginary gives you sines and cosines. So, and that's going to be the square root of that, will be the coefficient. Right? So I better call this a square of something. So I have a choice here of calling this a plus or a minus a constant x squared. The squared is important because I'm going to take the square root. Why the plus or the minus? If I use a plus, then I'll have an exponential of a real. If you use a minus, I have the exponential of an imaginary. And in that case, I get the sines and cosines. As it turned out, knowing the solution and having gone through it so many times, and we have generations before us that told us, don't pick the plus. Right? We're going to do more work. At the end, whatever you pick is going to lead to the right solution. The mathematics is solid and is going to give you the right solution. So if something arbitrary like that, right, the minus is going to save us some more extra work. So I'm going to call this minus kx squared, minus ky squared. For the z, as it turned out, that you can go either way, plus or minus. And the reason for that, as we learned in transmission lines, is actually the exponent is complex. The exponent of the coefficient comes out to be gamma alpha plus j beta. So it has an alpha term and a beta term. And the alpha gives you the amplitude decay, and the beta gives you the sines and cosines. Well, when you think about it, where will the losses come from? We have source free, we have ideal conductor, we have an ideal dielectric. We wrote epsilon in our media, we didn't write epsilon star. Right? There's no complex epsilon or complex mu that we wrote in the operation. We assumed that kind of thing in the beginning. So likely a minus will do. But like I said, you can pick either one. Right? How about if I call this K squared? A matter of convenience. They are all K's. So if I pick this to be minus K squared, let's just write one of them. So what's Fx looks like now? Something times e to the j kx x plus something else times e to the minus j kx x. Right? Because if you take the square root of this, the square root of that here is going to give you plus or minus j kx. So you have one with a plus j and one with a minus j, and what you do is you mix all possible solutions. That's the rule in general solution. When you do a general solution, you find all possible solutions and you just mix them up. And let the boundary conditions decide for you how much are these parameters. So you can call this something, call that something, and add them. You can do the same thing for all of these. That's what we're going to start with next time we do Wednesday. Any questions before we go?
Will you be by your computer, I guess? Because you said we should send you emails if we have questions, so that assumes in the 3 hours we're taking the test, you're at your computer ready to go.
That's a good question. You are right. I didn't think about that one. Also, I didn't think about the fact that if you ask me a question, I'll answer you, and the others have not started yet. So, logistics. I don't have an answer. Well, how do we overcome this one here? I got myself into a hole.
Automatic A's. Automatic A's for everybody.
That's a good. You could say, we can take a break if we have a question with your email, and you would respond.
All right, assuming that you don't, do anything in between, like get other resources, okay?